recording. So I will record this because I think everybody cannot be here today. I think a couple people told me they had stuff going on. And thing is, you already have the answer key. I want today to be interactive. I want you guys to tell me. Now, like I said, the first few problems, you're just pushing buttons on a calculator. There's nothing that you have to know other than C, big P, right? Where's the exclamation point key? Stuff like that. So going back, I want just the first four problems to just kind of get us warmed up. But I'm going to ask you things of this nature. And I'm just going to say, do the calculation. You have to get these right because there's nothing to do. You just enter it in the calculator. Do you notice on 2 and 3 and 4, I did not actually use the factorials. I'm simply using my calculator. Number 1, I had to use the factorials because it's too big for any calculator to do, really, unless you have a, titanium like I do. But, that's a special calculator. But most people don't have one of those. Now, can anybody tell me why number 4 is 1? Yeah, I know the calculator said it's 1, but can you explain why those? By the way, for the quotient to be 1, doesn't that mean that numerator has to equal denominator? That's the only way it can be 1. But I asked 2 different questions. So this is really understanding combinations, if you can tell me the answer to this one.
They're on opposite ends of the probability distribution.
Okay. So when we make that probability distribution, we often see the same on the binomial distribution, the Pascal's triangle. I think that's what you're referring to. Do you everybody remember that, how the numbers kind of go symmetrically? But there's actually an easier way of thinking about it. I've got 12 people in a room and I want to take 3 of them to lunch. How many ways can I do that? You'd say combination 12, choose 3. I got 3 people in a, excuse me, I have 12 people in a room and I want to leave 9 of them behind. How many ways can I do that? Combination 12, choose 9. But in leaving 9 of them behind, isn't that the same as choosing 3 of them? Think about that. Choosing which 3 to take with me is exactly the same as choosing which 9 to leave behind. That's why it's the same thing. And remember, the formula for combination n choose r, remember, is n factorial, n minus r factorial, r factorial. So in the statement, it's a little bit of glare, isn't it? Okay, you know the formula. So in the statement, 12 choose 3, isn't my denominator 9 factorial, 3 factorial? And in the statement 12 choose 9, my denominator is also 9 factorial, 3 factorial. So that's why they are the exact same number. I like what you said, Salvador, that it's when I'm looking at the distribution, it's the same in both directions. That's why the first and last numbers were always 1s. Then the next, moving in. That's an easy way to conceptualize it. But in the explanation, choosing which r things I want to take with me is the same as choosing which n minus r things I want to leave behind. That's a really simple way to justify that one. Now, let me go back. Go to here for a moment. So hold on, I'm now going to go to the practice test itself without answers. I want you guys, I know you have the key, but I want you guys to tell me what and how. Let's take a second here. All right. So now, next ones obviously are permutation, combination kind of questions. So rather than tell me the number, tell me what I'm going to do and why. Because if you tell me combination, 20 choose 10, well, I know how to enter that in my calculator. But if you tell me permutation 20 choose 10, I know how to do that one, but that's a different number. So does anybody, and I'm hoping you're all unmuted unless you have a screaming baby in the background or something. Can anybody tell me on number 1? We have 45 people in the math club, and we're going to select a president, vice president, secretary, and treasurer. So everybody can be president, but not everybody can be 2 things. So we're going to choose 4 different people. First of all, is this a combination or a permutation?
Permutation.
Well, too many voices. So what was it, Rosalind?
Permutation.
Why is it permutation?
Because order matters.
Good, because being chosen president is not the same as being chosen vice president. If I said I'm taking 4 people to lunch, doesn't matter what order. But you know what? You being president is different than you being secretary or you being treasurer. So it is a permutation of 45 choose 4. Now, you don't have to do that. You have to enter that into your calculator. And everybody, when I enter my calculator, 45P4, my calculator says really big number, over 3 million. Wow, that's a lot of possibilities. But I didn't have to write them all down. I just had to calculate them. Now, my 119 math club with 45 students, I want a basketball team. We're going to go play the calculus club next week, okay? So how is this a permutation or a combination when I select my basketball team? Everybody, what do you think? Permutation or combination?
Combination,
Why?
because
it
there's
doesn't-
no order.
Good, order doesn't matter, just being selected matters. And by the way, if you understand that from 5 and 6, you can get every possible permutation combination question. There's no ambiguity. I'm picking 5 people, so if you're picked first, third, fifth, doesn't matter, you're picked for the team. So therefore, the answer is 45, choose 5, but it's a combination. Now, I changed the way I asked the next question. We want to form a softball team. Okay, and a softball team, you generally have 9 people out there, like baseball. There's gonna be 9 people out there. So we're gonna select our 9 people, but we want to create a batting order. So if you've ever played or watched a baseball game or a softball game, right, you're first up, you're second up, you're third up, you're fourth up, whatever, up to the 9th up. I have 45 people and I want 9 people in a batting order. How do I do that? Is that 9 factorial? How do I do this problem?
Permutation?
Permutation of 45, choose 9.
Yes.
Yes.
I have to select the 9 people. Remember, there's 45 folks. I have to select the 9 people. And am I putting them in order? Well, let's see. It's called a batting order. So yeah, if you've ever played softball or baseball, being up first and being up 9th is not the same thing. I'd rather be up first,
Okay,
get them off.
Professor,
Yes,
for me, when I did this one, I got a,
you got a
got-
scientific notation answer.
yes.
That's because your calculator, it had too many digits. So
Okay.
now compare your scientific notation answer. Hold on a minute. Let me stop sharing this one. Oops, go back. I'm gonna go back to the key one.
Well, I also got a decimal, that's why.
Well, no, you got a scientific notation. Whoops, I can do what I wanted to. Hold on a second. I think I lost my original one. Is this my key? Hold on. Should have. This is the right one. Okay. Now look at this is the actual answer. Look at how many digits: 3, 6, 9, 12, 15. Your calculator is not capable of 15 digits. Most calculators 11 at the most. So what it did was it said 3.2 something something something. Correct?
Yes.
And then
Uh-huh.
how many digits did it move?
Oh, my gosh.
How many digits are there to the right of 3? Well, we said it was 15 altogether. So there's 14 digits to the right of 3. That's why it says times 10 to the 14th power. That's
Yes.
so you understand the translation. Scientific notation people think is an evil ploy. No, it's because when you're dealing with astronomically big numbers, trying to write down all the digits can be difficult. In fact, calculators really can't store that many numbers. So the scientific notation answer is just kind of a shortcut way of saying, hey, this number is really, really, really big, and we can't fit all the digits on your calculator screen. So we're going to tell you how many digits they're supposed to be. So after the 3, there's supposed to be 14 more numbers. That's what the times 10 to the 14th part tells you. That's it. That's it. Now, if the number were smaller, like problem 5 and 6, you don't need it. So if this were the question and your calculator gave you a scientific notation answer, you can give a scientific notation answer. I'm not going to ask you something that's big. I just wanted to illustrate. That's a silly big number. Now, if you start from the right, okay, see, first 3, then I'm in the thousands, then I'm in the millions, then I'm in the billions. This answer's in the trillions. 321 trillion, 570 billion, 878,400,000. If I'm the coach, that's a lot of choices, isn't it? I got to put together a team. I don't want to be coach of this team. Too many choices. That's kind of silly at the point. Now, talked about fair games all over the place. We did it with lotteries and we did it. This is the easy one. This is just rolling a simple die. Now, oh shoot, sorry. I don't want the key. Sorry. My share screen keeps switching on me. Which one's which? Every time I go to the share screen, that I have two on there. I have the practice test and I have the key, and each time I do it, they keep flip-flopping their positions. So this one here is, we're going to play the dice. We're going to play the roll of the die. Okay. Now, we want to make it a fair game. Games aren't fair unless you make them fair. So you're going to pay $100 to play. It's only going to be a fair game if on the average you walk away $0 richer, $0 poorer, which means you have to win some of the time, obviously, because you're paying $100 to play. So if I pay $100 to play, so if I roll a 1, 2, or 3, I win 125. That means I come out $25 ahead. Everybody agree?
Mhm.
I've made $25. If I roll a 4 or 5, I get paid 80. But that means I lost $20 because I had to pay 100 just to play the game. So the first 3 outcomes, 1, 2, and 3, I walk away ahead. 4 and 5, I walk away behind. So the question is, exactly what should the payout be on a 6 for this to be a fair game? Now, here's where it gets a little bit tricky. The numbers 125 and 80 don't actually figure into the answer. It's 125 minus 100 and 80 minus 100. Does that make sense? So the outcomes that I'm going to get, go back to the, no, this is, you guys are getting busy. I keep switching screens on you here. Let me go ahead and pin myself so it's a little bit bigger. The possible outcomes I can get, I have $125 win, but I paid $100 to play, so it's only a $25 win. I win $80, but I had to pay $100 to play, so I actually lost $20. Okay, and then the last one, I don't know, let's just call it Y. Y dollars, because I don't know, I have no idea what it is. But here's what I do know. What is the probability of the first one? Well, it was the roll of 1, 2, or 3. So that's 3 of my 6 rolls. So the expected value of X would be 25 times 3, 6. Plus negative 20 times what? How many of the rolls will I have that outcome? Anybody? If I roll a 4 or a 5, so how many rolls is that?
2, 6.
So 2 rolls, so 2, 6 would be that probability. And then finally, the X or Y, whatever that is, times 1/6. And I need this to equal 0. So the easiest way to do it, since they all have a denominator of 6, just look at the numerators. 25 times 3 is 75. Negative 20 times 2 is negative 40. So far I am 35 ahead. So I need to be 35 behind. I need the Y value to be negative $35. Again, 25 times 3 plus negative 20 times 2 plus negative 35 times 1 would add up to 0. So I need the outcome of the last roll to be losing $35. So what should the payout be for a 6 if I'm losing $35? Remember, you had to pay $100 to play. Anybody? Without looking at the key? How do I lose $35 if I had to pay $100 to play? By paying you
65.
$65. Yeah. You've lost $35 if you only win $65 because you paid $100 to play. So there's outcome I can have. Now, if I go back to the beginning of the problem.
Wait, how did you get negative 20?
I'm sorry, say again?
How did you get negative 20?
Well, actually, how did I get 25? Because it's the same way. How did I get 25?
Yes, that's my question too.
because you paid $100 to play. And then when you won, I gave you 125. You didn't win 125, you won 125 minus the $100 you had to pay to play. Remember, what are you walking away with?
Okay.
See, it's like a slot machine. I won some money, but I also had to pay to play. And so I have to take the
Hello.
amount I won and subtract the amount I
Okay.
had to pay. So if you're paying to play and you don't win at least that much back again, then overall you've lost money. If you pay to play and overall you win exactly that amount coming back, then you walk away with zero. You didn't win or lose. So that's the idea. You paid $100 to play the game. You gave the dealer $100. Now you rolled your die and you got a 1, 2, or 3. So they're going to hand you $125. You're like, wow, I won 125. Yeah, but you had to pay 100 to play. So you really are only walking away $25.
I see.
there.
Okay,
Does that make sense?
yes.
Okay, so now when I rolled a 4 or a 5, you got paid 80, but I paid $100 to play. So now I'm $20 in the hole. So
Okay.
if I roll a 6 and you pay me $65, great, but I paid $100 to play. So that means I'm 35 in the hole. Yikes. But now when I do the expected value of these guys, 3 6 times this plus 2 6 times this plus 1 6 times this, that adds up to 0. So it's now a fair game. I can win some of the time, I can lose some of the time, but over the long run, this is the way of thinking about it. If we did this over and over and over again, I'm breaking even overall. That's really what that means. I'm going to break even in the long run because my probability of winning and losing and the expected value is exactly 0. So it's a fair game, which means on each individual try, I might win or lose. It's like a coin flip. I might get a heads this time, but I might get a tails next time. But overall, it's going to probably balance out the number of heads and tails. That's the idea of a fair game. So let's go back to, here we go. Now, the next one is a probability distribution question. Hopefully, we've gotten pretty good at these. This is not a coin flip. This is not a roll of a dice. This is just somebody kept track, right? And let's say that from the census, the nice thing is I don't have to know how many people there are. The probability of 0 cars is 0.06. That means 6% of the people have 0 cars in their lot. 23% of the people have 1 car, and so on. Notice the probabilities have to add to 1. That would be a problem if they didn't add to 1. So the probability distribution, I want to start with the histogram because that doesn't require any calculation or any work. So in my histogram, it's extremely important that I make it readable. The highest probability you see on there is 0.42. So that's about how high my histogram should be. I don't want to make my histogram, go from 0 to 1 and then have all my rectangles be really, really tiny. So I want to do something like this. Okay. Now, I don't know if you guys can all see because of the glare, but let's say 0, 1, 2, 3, 4, 5, 6. Now, because 0.42 is the highest probability, then I want 0.4 probably somewhere at the top. So this I'll call 0.10, 0.20, 0.30, and 0.40. Then 0.42 would just be a little bit higher than that. That makes it a little easier to read. And now I'm just going to make my rectangles. The first rectangle, 0.06, so not quite all the way up there. Something like that. My second rectangle was 0.23. I'm going to make it, and then I'm going to come back to my screen. I have to be able to read it. It's right in front of me. So 0.23, about there maybe. The next one is 0.42, so that's really tall. The next one, 0.17, about there. The next one, 0.08, a little bit less. Oh, I said 6. There's only 5 seconds. It doesn't go to 6. And then the last one, 0.04, maybe about there. All right. So my beautiful histogram looks something like, okay, 0.1, 2, 3, 4. So 0.42 is a little bit higher than that. but that way I can easily see, and you can see, the bulk of the outcomes are here. There's no calculation here. I'm just drawing the picture from the data. The calculations will now be from expected value and variance. Now, I remind you, we know what expected value is. Expected value is the sum of the outcomes times their probability. And in shorthand notation, just that. So the outcome of 0 times its probability of 0.06, the outcome of 1 times its probability of 0.23, and so on and so on. The variance is a very similar calculation, as we know. We know the variance uses the same numbers, same probabilities, but now I square each outcome times its probability. And then in the end, what was the last thing I always do? The one thing we often forget?
Subtract.
Keep going. Subtract what?
The mean.
You're right. Subtract something. Subtract what?
Mean.
The mean?
No, the expected value.
Well, the same thing, but is it just the mean or the square of the mean?
Oh, square of the mean.
Square of the mean. Now you have these formulas. I'm going to show you where they are on the formula sheet. So you can, by the way, if you choose to write down your own formulas, that's fine. Probably be wise to print out the formula sheet because they're already there. But if you're looking at the formula sheet and it just looks too mathy and you say, you know what, I kind of want to put it in my own words, that's okay. Just make sure you're not changing the formula because then you would get an incorrect answer. So when I do this on my calculator, go back to my picture again. When I do this on my calculator, notice what I have for expected value. It's like I just said, 0 times 0.06 and then plus 1 times 0.23 and so on. From the probability distribution, I took the outcome 0 multiplied by its probability plus the outcome of 1 times its probability all the way to the end of the line. That's it. There's no interpretation. I just do that act and hopefully you get 2.1. Now 2.1, if you go back to the picture, you go, yeah, that makes perfect sense. So hopefully that was an easy calculation. The variance calculation, I tend to like to do the variance right under the expected value because in the variance calculation, I'm using all of the exact same numbers, but the big difference, I'm squaring the x's this time. So hopefully you can all notice that. Expected value, you see 0 times 0.06. For variance, you see 0 squared times 0.06. All the way down to the end of the line, I get the last one, 5 squared times 0.04. And then, like you said, the final thing is to subtract the square of the mean. That's why you have to do expected value. That's the mean. You have to do that one first because you're using that value to do the next one. Now, those are just straight up calculations. We want to make sure we're doing it correctly. Does anybody have a question on either one of those calculations? We have done this now for a few weeks, so hopefully, this is good. I would also strongly recommend, because it doesn't take very long to do this calculation, do it 2 times. Okay, do it 2 times, and if you get the same answer, you know you did it correctly. Okay, is everybody on board with that one? Just be safe. It doesn't take very long, but if I press a button, decimal places, if I get it off by something, when I do minus the square of the mean, did I forget to square it maybe? There's a lot of things we know what the right thing to do is, but there's a lot of things we can make mistake on the entries because we were just fast. So always do it twice because it doesn't take very long to do it. And then when you get the same answer twice, you know you did it right. Okay, any question on that? And of all the things we did, expected value and variance is probably the thing we've done the most on this test. Okay.
Professor,
Yes.
did you mention, because I'm looking at the formula sheet and
I'm
you're right.
gonna go back to that. I'm gonna wait to go back to that because that means I have to open up another. Well, I guess I could.
Oh, okay.
Now.
All right.
Just it's the opening of the document. It takes a little bit longer.
Well, my question was, just looking at it, it looks a little bit more complicated than what you wrote on the, so I like that you said we can write it our own self.
What I'm gonna do is, when we get done with this, I will close these documents and then I'll go in and I will open it. But I have to do that separately. Just
Okay,
And then I'm gonna go over the formula sheet because there's a lot of
Okay.
formulas on there that we haven't got to yet.
okay, thank you.
Do you remember the first time we looked at it, how scary it was? And then I showed you, well, we're only going to here, and everyone said, oh, okay, well, I can deal with that. You know, I know these, I've used them.
Yeah,
What we're now doing is we're gonna go a little bit further, but
Okay.
only a tiny bit further, because there's still a lot of things there we haven't gotten to yet.
yeah,
And
it
you're
looks
looking
scary.
at it, when you're looking at it as a whole, you know, you run for the hills, right, in terror,
Yes.
right? It's like a scary movie with the person coming at you with the knife, you know, eek, 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 you know, the high pitched
Yeah.
violin, you know,
Mhm.
psycho shower scene. I don't want any of that. Yeah, that's
That's what it
I always
looks
do
like.
that. My calculus classes, they always know the eek, 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 you know, big old blade in your hand, you know, crazy person. Usually they've got some kind of a hockey mask and a chainsaw, and you know,
Yes,
want this not to be scary. Okay.
okay,
Scary no work, as we say, scary no work. So I took these numbers, I just added them up and multiplied. That part 9 and 10 is supposed to be simple because you don't have to think about it, you just do it. Drawing the histogram doesn't help you answer that question. I think drawing the histogram sometimes makes the answer make a little bit of sense. See, in our histogram, isn't the highest rectangle 2? Everybody, isn't that the case? Our
Yes.
histogram, what did you just calculate the expected value of X to be, which is the mean? You calculate it to be 2.1. Does that kind of agree with your picture? Yeah, it totally agrees with your picture. And your variance is not very big because, you know, this is kind of tightly clustered in the middle. Now, variance is a little harder to interpret in some cases, but everything you did was correct. The histogram is not necessary for the calculation. I just think the histogram sometimes makes the calculation easier to comprehend because you got a calculation where it said the mean was 2.1, and you have a picture where clearly 2 is the highest outcome, you know, and then there's a few outcomes to the right of 2. So yeah, a little bit more than 2 makes sense for a mean. Okay, now we're going to do the binomial problems, which at this point, most of you have gotten really fast at and really good at. Okay, so let's go back to that. Make sure I'm at the right one. Okay. All right, so now we're going to do a multiple guess test. There's an 8-question multiple guess test, A, B, C, D. And, you know, only one right answer. A, B, C, D. You walked into the test, you got your time wrong, you forgot to change the clock is what happened. So it was an hour-long test. You walked in 1 minute before the end of the test. Okay, because you got your time wrong. And so you quickly just filled in eight bubbles. Everybody got it? That's all you did. You just quickly filled in eight bubbles on the multiple guess test. You didn't even have time to read the questions. Are you going to miss all 8?
No.
What do you think?
No.
Probably not, actually. The probability of missing all 8 isn't very good, by the way. In fact, that's what I'm asking you on. Did I ask you that somewhere? Oh, actually, no, that's the next one. The probability of missing all 8, I will tell you exactly what it is. It means getting the wrong answer all 8 times. The probability of that is actually only about 0.1. The probability that you walked in, guessed on all 8 and missed all of them, it's only about 10% likely to happen. No, you're probably going to get something right. Okay, so what we want to do is make a table for the probabilities. Now, this is long. We've done this before, and most of you have got this. What are the 3 key numbers I need? What are they?
N,
N,
P,
P.
and
Q.
Q.
Can I get those from the problem?
Yes.
yes,
Okay, what is N?
8.
8.
8. What is P?
1/4.
1/4. Beautiful. Therefore, automatically, what is Q?
3/4.
0.75.
Now, I'm glad you said that. When I'm entering these into my calculator, what is easier to enter, 1/4 or 0.25?
0.25.
Yeah, because the 1/4, I have to go parentheses 1 divided by 4 close parentheses. That's 5 things I have to do. If I miss any one of those, I'll get an error message at the end that something went wonky. But if I use 0.25 instead, do you see how that would be? It just makes the calculation simpler. The answer is P is 1/4. But I would suggest using 0.25. It's less button pushing and less likely to have error messages. So if I have that, I'm on the way. What did I do? Here's my eraser. So when we make our probability distribution, what I need to do now is use that formula, the formula for calculating the probability. Remember what it is? The probability of any particular outcome, we said, is combination n choose x, p to the x power, q to the n minus x. X is the number of successes, n minus x, therefore, would be the number of failures. In this case, since n is 8, 3 successes means 5 failures. 7 successes means 1 failure, and so on. So the exponents on the p and the q have to add up to whatever n is. In this case, n is 8. That makes it a little bit easier. So I need to find the probability of 0, 1, 2, 3, 4, 5, 6, 7, or 8. That's not a short problem. Okay, that is a little bit of work, but part of the reason you're doing this is to be able to manipulate that formula. So let's just do the first few. We don't need to do all of them. If you can do the first few, you can probably do all of them. So what is the probability of 0? That would be combination 8 choose 0, 0.25 to the 0, 0.75 to the 8th. Okay, everybody got that? So let me go ahead and put myself back on here. So probability of 0, n choose the number of successes, probability of success to the 0 power, probability of failure, right? That's what we just said. And that number there is actually very small. That's the probability of missing all 8, getting 0 correct. And that number is approximately 0.1001. Wow. It's not very likely that I miss all 8, is it? So now let's do the probability of 1. The probability of 1 is combination 8 choose 1. What am I going to multiply that by? I mean, look at the one above it.
25
Or no,
to the power of 1.
2.5 to the power of 1, and then 7.5 to the power of
7.
7. Okay, 0. This is critical, folks. This is the easiest part, but the most important part. 0 right means 8 wrong. 1 right means 7 wrong. But the probability of success and failure is still 0.25 and 0.75. That didn't change. I'm still 8 choices, right? I just keep, all I'm doing is upping from 0 to 1 to 2 to 3 and following. So this one here would be 8 times 0.25 times 0.75 raised to the 7th. Wow, this probability is significantly higher. I'll put it over here. This is 0.26696. So to 4 places, it would actually be 2670. Wow, that's way more likely. The probability of getting none right is only 0.1. The probability of getting exactly 1 right, that's more than a quarter, isn't it? More than a fourth. Now, let's do one more. What's the probability of getting 2 right? For the probability distribution, I would do all 8, but I'm guessing if you can do the first few, you could do all of them. This is combination what? Walk me through it. 8.
2.
8 choose 2.
To the power of 2.
And to the power of?
6.
Yep. Once I start it, it kind of self-navigates. At the end of the line, if I did all of the probabilities, 0 through 8, tell me something about those probabilities as a whole. They have to
Equal 1. Up to 1.
Exactly 1, because I've covered all my bases. So this one here, 8 choose 2 squared times 0.75 raised to the 6th. This probability, oh my goodness, 0.3115 to 2 decimals. Wow. Now, if you look at these 3 answers, 0.1, 0.26 something, 0.31 something, if you add up those 3 numbers, you're well over 2/3 at this point. I can get 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. There's a lot of different outcomes, but just the outcomes of 0, 1, and 2, almost 70% of the time, when I add up those probabilities, I'm going to be 0, 1, or 2. All the successes are at the beginning. Why? Because it gets harder as I go along. Is it possible mathematically to get all 8 correct? Is that possible?
Yes.
Yes. Is it likely, do you think?
No.
No, and the probability, I'll tell you, it's exactly 0.25 to the 8th power, which is 0.000015.
Yeah.
Again, that's the whole getting hit by lightning thing. I don't know which one's more likely. Is it possible? No. Excuse me. Yes. Is it likely? No. We have to understand the difference. If we say something is not possible, that means it has a probability of 0. If the probability isn't 0, then it is possible. That doesn't mean it's likely. Does that make sense? Is it possible a team of 5-year-old basketball players could beat the Los Angeles Lakers? Well, if you've watched the Lakers lately, I don't know. Maybe. Okay, so you say, no, that's not possible. But what if we set up the game and the Lakers bus was delayed in getting there, so the kids win on a forfeit? I mean, think of something silly like that.
Yeah.
Oh, yeah, I guess it's not very likely, but I guess there's a way it could happen, If it's not possible, probability is 0. Those go hand in hand. If the probability is not 0, then it is possible. But we still can be smart and say, it might be possible, but it's not very likely because the probability is so small. 0.1 is 1/10. 1/10 is not a very large probability, but it's far from impossible. Okay, it's not very likely, but it's far from impossible. So that's one way to imagine things. So now I asked you a question about range rule of thumb, and I love range rule of thumb because it is it's not the but it's a common sense thing. So you've made this table, and now when I ask you for expected value and variance, we know how to do it. Again, I do the sum of the outcome times the probability, but we now know a shortcut, don't we? Everybody, do we know a shortcut for expected value and variance in this case?
Yes.
We couldn't use a shortcut in the last problem where I gave you a number of cars per household because that's not a binomial distribution. This is binomial because there's 2 outcomes. I got the question right, I got the question wrong, and the probability of getting it right is always 1/4. The probability of getting it wrong is always 3/4. That makes it binomial. Binomial because there's 2 outcomes, the probabilities don't change, and I'm going to do it a certain number of times. When you have a binomial experiment like this one, expected value and variance, oh, you love them. What is the expected value in the binomial case, we said? NP. What's the variance in the binomial case? Do you remember? Without looking at your notes or homework? Or
Wait, what was the question?
NPQ.
NPQ. Expected value, if it's binomial, is just NP. That, by the way, if you don't love that formula, there's something seriously wrong. I know I like doing it the long way. I like making the entire probability distribution, then multiplying everything out and adding them up and making lots of calculator errors and doing it 3 times. I love doing it that way. I don't know about you, but I like this because it takes me about 1 second. And the best part is I can't possibly mess it up. So in this problem, remember, you said N was 8, P was 1/4 or 0.25. It doesn't matter in this case. Q was 3/4 or 0.75. So for this problem here, what is the expected value?
2.
2. Here's what you love about that. Okay. The probability of guessing correct is 1/4. If I guess on every problem, it's kind of a common sense thing. Shouldn't I get about 1/4 of them correct? Doesn't that make sense to you? If I just randomly guess on every problem, I ought to get about 1/4 of them correct. When we looked at the probability distribution, the highest probability, by the way, just a moment ago, I think it was 0.31 something. The highest probability is actually getting exactly 2 correct. That's by far the highest probability. But also, if I calculated expected value by using all the numbers, it would have come out to exactly 2. But the common sense, if the probability is 1/4, then I ought to get 1/4 of all the questions correct just on the average. Okay, again, that's called the law of large numbers. If I do the same, if something has a certain probability and I do the same thing over and over and over and over and over again, I should see that probability applied to the overall. So it's like a coin flip. I should get heads half the time and tails half the time overall. What's the variance for this problem? What is NPQ?
Oh, 1.5.
1.5. Now, I don't use variance in the calculation. I use standard deviation. So lest we forget, how do you go from variance to standard deviation? Do you remember?
Square root.
Square root. Variance is the square of the standard deviation. Variance is sigma squared. Standard deviation is sigma. So to get standard deviation, I have to take the square root. So the range rule of thumb in simple English says the range rule of thumb, I ought to get 2, and I'm going to write it this way because that's how we say it, plus or minus. That gives me the cushion above and the cushion below. I should get 2 plus or minus what? 2 times the variance, which would be the square root of 1.5. Now I need a calculator for that. So what is 2 times the square root of 1.5? Anybody? About how big is 2 times the square root of 1.5? About.
2.1 or 2.45.
It's about 2.45. So the reasonable range of outcomes would be 2 plus or minus 2.45. So 2 plus 2.45 would be how big? If I use the plus, it'd be what? 4.45? Do you agree?
Yes.
If I use the minus, it'll be negative, won't it?
Yeah, but it can't be.
Can't be negative, so therefore, what should my lower end be?
0.
0. That's, by the way, I don't want to say it's an oh duh, but I can't have a negative number of right answers. I would have to write the worst test in the world for the instructor at the end of the test, not to give me a 0, no, to give me a negative percentage. Mr. Brown, your test was so bad, we're going to give you negative 20% on your test. You realize the absurdity of that. No, I don't think you could get worse than 0%. So because the range rule of thumb actually would have taken me on the other side of 0, we just say no. To get between 0 and about 4.5 right answers is what I would expect. Is it mathematically possible to get 8? Yes, we saw it was ridiculously small probability. Is it possible to get 7? Yes. 6? Yes. 5? Everything's possible. But the range rule of thumb says, you know what? Between 0 and 4.5. You said, well, you can't get 4.5. Well, let's say a large group of people were taking this test. Okay, some people will get 4, some might get 5. It's kind of an average. But for us individually, getting between 0 and 4 correct is a reasonable range. 4 would be pretty good, I think, since I'm guessing on everything. So now the last question of this cluster, this is now, it has to be an oh duh answer. It has to be. Is it reasonable to get more than 5 correct? More than 5 would be 6, 7, or 8. Is that reasonable? Based on what you just said. If we just said a reasonable range was between 0 and 4.5, then is it reasonable to get more than 5?
No.
No, we're way outside the range. 6, 7, and 8 are way outside the range. 5 is even outside the range. I said more than 5. So the answer is no, you're outside of the range. It's actually that simple. We want to keep it that simple because that's it. So figuring out using the range rule of thumb requires a little bit of work. I have to remember what the formula is. But now to ask you if an outcome was reasonable should be fairly simple. Let's go to the next cluster, which is, I'm going to do the same multiple guess test this time. Now I'm not going to come up with a probability distribution because with 100 questions, it would be too difficult plus too long. I'd have to have 0 right, 1 right, 2 right, 3 right, up to 100 right. That would take me a while, maybe a few days. So here I just want expected value and variance. this is exactly the same as the previous question. I just gave you a really large n. So all I have to do in order to answer this question, and you guys told me last time, I have to correctly identify what three things?
N, P,
N, P, and Q. So what's N?
100.
What's P?
1/5.
1/5. Can I conveniently convert 1/5 to a decimal?
Yes.
Yes. Do I have to? No.
No.
No, I don't have to at all. But if it makes, by the way, you're not doing the probability distribution. So you're not going to be raising it to powers and doing all that stuff. So if you want to leave it as a fifth, absolutely correct. Therefore, what would Q have to be?
4/5.
4/5, because that's what's left over. And again, lest we forget, P plus Q has to equal 1, because you are successful or you're not successful. There's not a third option. And so those probabilities have to add up to 1. So if I take this and I use the last thing we just did, then the expected value, and I'll write it out just to remind us. The mean of the population is the expected value of the random variable. We use them interchangeably, but the formula for expected value is to add up all these things. We now know that's also the same thing as the mean. So if you said mu equals, or you said expected value equals, you're saying the same thing. Just make sure you understand that they are exactly the same thing. So this is what? 100 times 1/5, and what does that equal?
20.
20. And again, if I ask you 100 questions, and there's A, B, C, D, and E, and I just close my eyes and randomly guess, I should get about 1/5 of them right. If I get more than 1/5 of them right, that would mean I'm a good guesser. Seriously, I'm a good guesser. That's all that would mean. If I get less than 1/5 of them right, then I'm not a very good guesser. I should get about 1/5 of them right, because I'm guessing on every one. What is the variance, which is sigma squared? 100 times the 5th times 4/5. And what does that come out to be?
16.
Exactly 16. Ooh, that's a nice number. You know why I like 16?
Why?
Because it's a perfect square. And what number are we going to actually use for a range rule of thumb? We're going to use its square root. Ooh. So what is sigma in this case? Well, it's the square root of sigma squared, or the square root of 16, which is simply 4. Do you like that? Yeah, you should like that. That's a great number. So the range rule of thumb says the reasonable range of outcomes, not the only possible. If there's 100 questions, it's possible to get all 100. It's possible to get 0. Everything's possible. But the most likely outcomes, the reasonable range, is plus or minus 2 standard deviations. What's 2 times 4?
8.
So that means, what was the mean? The mean was 20. So basically this means the range rule of thumb says 20 plus or minus 8. That's what it says. 2 standard deviations. So 20 minus 8 would be what?
12.
12. 20 plus 8 is?
28.
The reasonable range is anything from 12 to 28. That's what range rule of thumb says. Is it mathematically possible to be outside the range? Of course it is. But the vast majority of all outcomes, if I added up their probabilities, it'd probably be more than 95% of the outcomes are in that range. It's mathematically possible to be outside that range. It's just not very likely. So the last question of this cluster.
Wait, how did you get 8?
What's the range rule of thumb? We've been doing it now.
2
2 what?
times.
2 times the standard deviation.
Okay.
Plus or minus 2 times the standard deviation.
So then
the
if you
last
were to
problem.
write it out, it would be 20 plus or minus square root of 16.
2 times the square root of 16. Yeah.
Okay.
In the last problem, that was a decimal value. Because we did 2 times the square root of 1.5, and that gave us about 2.45, remember?
Mhm.
But we did 2 times the square root. Okay, now we're doing 2 times the square root of 16, which is, I like that better because I don't need a calculator at that point. It doesn't change how we do the problem. Okay, so hold on a minute. I keep going to, sorry, they keep flip-flopping on me. I mean, key will be on the left of my share screen, and then the next time it'll move to the right, depending on which one I select. So, okay. So, your friend says they guessed 40 answers correctly. That is mathematically possible, and on a 100-question test, 40 is not very good. But if I'm guessing on every question, is 40 very likely? What do you think? Is 40
No.
very likely?
No.
No. In fact, you can give me a very specific answer. The standard deviation is 4. We said the range rule of thumb says the vast majority of all outcomes happen within 2 standard deviations. That's why you did plus or minus 4. But in reality, as we've been seeing from the normal distribution, it is extremely rare to ever be more than 3 standard deviations away from the mean. That's extremely rare in any scenario. If the mean is 20 and the standard deviation is 4, then the outcome of 40 would be 5 standard deviations, 5 times 4 above the mean. Does that make sense? To be 5 standard deviations above the mean is not absolutely impossible, but again, you're probably more likely to get hit by lightning twice today. It is so extremely difficult. Yeah, it'd be like 1 out of a bazillion. So 40 is not reasonable. 40 is ridiculously far from reasonable. And because you have the range rule of thumb, that's what makes it really, really nice. Now, you can do these questions. So what have we been doing? We did basic calculations with factorials, permutations, combinations. We answered questions where we had to interpret, is it a permutation or a combination? And most of you guys just kick butt on that. We have probability distributions, and then we find the expected value and the variance. They have to be calculated. There's no shortcut. Then we looked at binomial experiments, where we can calculate the individual probabilities, and we can also do the expected value and variance really, really fast. And then ultimately, we have the range rule of thumb. So what I want to do here, and take me a moment, I got to go back to Canvas. So give me just a second. I'm going to go, have to go kind of a different way around here. Oops, hold on. There. I'm going to bring up formulas. Okay, now. You know, I never used to be able to do this kind of stuff in a classroom setting. It's just so convenient now. Is this the right one? Hold on, here we go. All right, so on the sheet here, if you look, these were the formulas we did the first test. Here's some of the probability things. Remember union and intersection, and you guys did a pretty good job at that. Conditional probability. Now, going down here, permutation, we know that. You don't have to enter the factorials, you just have to know which keys on your calculator. Ignore the base term, that's a typical stats class is going to do that. We're not covering that one. Probability distribution. Expected value, see that? Sum of the outcome times the probability. That's exactly what I was talking about earlier. Variance, same thing, but it's the outcome squared and then minus mu squared. We did that today. We've already looked at it. Binomial probability. This weird thing in the parentheses, that's the same as combination. This is the same thing I use for the regular stats class. They sometimes see different notation. Now, notice this is binomial mean, binomial variance, binomial standard deviation. We've done this like 5 times today. That's the end of the formula. Everything after that is stuff that's going to be on future tests. Everybody got that? So don't go past you see binomial. Oh, NP by variance, NPQ. Standard deviation, the square root of variance. We know that. We've been doing that today, and you guys have been just nailing that thing. The thing that says Bayes formula, ignore that. Again, we're not covering that in this class. So I want to show you from the notation standpoint. Everything up there is exactly correct. We have been using a simpler notation for combination. The universal combination notation, which some of you may very well have seen in another class, when we say, make sure you can see this, when we say combination N choose R, that's the way we've been writing it. It's also correct to write it this way. This is the way most of the textbooks will write it. So on the formula, I wrote this, but that's the same as this. It's exactly the same thing. In my calculus classes and stuff, I'll use this notation, but they mean exactly the same thing. So when you see the parentheses and the N and the R in that formula, just go ahead and write the big C in there, because that's all it is. Okay, is everybody cool with that?
Yes.
In
And
the
you said that we
textbooks,
can write our formulas differently, right?
I said, if you want to write on the formula sheet, by all means do so. Now, what's not on the formula sheet? What's the last thing we did in the last few problems?
The shortcut?
No, that's on the formula sheet.
No,
Rule
the
of thumb.
values.
The thing involving these guys.
Range rule of thumb.
Yes. So what's the range rule of thumb in words?
It's N.
No, in words,
It's
Majority
of
of
the
outcomes.
of a binomial experiment are within 2 standard deviations of the mean.
The mean. So it's the 2 standard deviations that you have to remember. So you're going to go plus or minus 2 sigmas. But the calculation of the mean and the sigma, for you guys at this point, that should be a slam dunk. The calculations should be easy. The range rule of thumb, you actually have to think about it, because now you're going to give words and say, it is reasonable that my outcomes are in this range. The last problem, we said it was reasonable that the outcomes were between 12 and 28. Doesn't mean it's impossible to be outside the range. It just means it's very unlikely. That's it. Never confuse the two. Improbable does not mean impossible, but it means it's probably not going to happen. Very unlikely. So that's it. You know what the test is going to be on. Now, many of you have asked me about the quizzes and the redos and things. If you did not turn in a quiz, or you had a particularly bad one and you want to give it another try, because you need to know this. Yes, this time though, I do want you to bring it. So a lot of you emailed them to me, and the problem is 3 weeks ago, some of you emailed them, and I have still not been able to open up your emails because you sent them in a format that's not possible for any computer to open. And you still haven't given me hard copies. So no, I want hard copies. If you want to redo one of them, say, you know what, I really didn't do well on this one, because those questions are going to be on the test. You need to be able to answer them. It's not the points. The points are meaningless. The test is worth 20 times the quiz. The points on the quiz are nothing. It's, can you get the answer right on the test? Well, if you didn't get it right on the quiz, probably not going to go as well on the test, because you don't get to bring all of your notes and homeworks and everything. You get to bring the formula sheet and a calculator. Okay, so I encourage people. Now, what if you got a perfect score on a quiz? Should you redo it for yourself? Anybody? Yes, to make sure you still remember it. If you did a quiz 3 weeks ago, is there any guarantee you're going to remember it on Tuesday? Maybe, maybe not, because as we move on and do other things, you forget things. Everybody forgets things.
Yeah, I forgot about everything.
Well, hopefully not everything.
No. I mean, I thought it was gonna be like harder, this one.
Well, remember, we're only testing on short bites.
Yeah.
The first test was covered 6 classes, but the first class, we didn't cover a ton of stuff. This and the next couple of tests only cover 5 lectures. So I'm keeping it in small bite-sized portions. And if you think about it, everything on this test is involving what? Permutations, combinations, factorials, probabilities. I mean, it's the same stuff. It's just how we're doing it. Okay. And making sure our answers, of course, make sense. And that, like I said at the beginning, let me change the view here. I want to see what you guys look like. It is very necessary that you have a calculator that you trust. I could care less what kind of calculator you use. But if you have to go dig deep through menus just to find your combination key, that's probably not as good a calculator. The one I like using, the one I've been loaning out in class, these cheap Casios, right? Everything is right here. I mean, this combination key, permutation key, they're right up there near the top. Factorial key, they're right up there at the top. I don't have to go to the menu. It's so easy to use. That's why I like using this one. I don't have to think about it. I just want to hit the button, hit equals, and know that I've done and can move on. Whatever calculator you have should be one you are comfortable with and that you're not second guessing. See, second guessing's bad. When you second guess, you change answers. And that means you might change a right answer into a wrong answer because you didn't trust it. You have to know, if you know what you're doing, you have to know that you entered it correctly under the calculator. But you're not doing these in your head. So you have to rely on the fact that you're hitting the right buttons. We're doing something as simple as a combination. That takes you a couple of seconds. But nobody in their right mind would try to do that by hand, would they? Because the answers are too big. So you have to know, did I hit the right buttons? Okay, that's it. And if you've practiced and you hit the right buttons, a lot of these problems will feel like slam dunks. And that's, by the way, that's a good thing. So what should you bring on Tuesday? Well, a calculator you trust. I will bring some departmental ones and I will loan them to anybody, but that means you're using an unfamiliar calculator to take a math test. That's not evil, but it's probably not the wisest thing. You want to use a familiar calculator to take a math test. Bring any reattempts on quizzes. Bring the formulas. Now, the formulas from the first test, we're not using any of those on this test. But if you want to say, let me just print the first 2 sheets and I'll kind of highlight what I know I'm going to use, maybe write in the range rule of thumb, write in the combination using a capital C just to make sure you know it. But the other formulas, in fact, I didn't just say to me, I said the binomial expected value, like hint, hint, wink, wink, nudge, nudge. Oh, binomial is NP. Only the binomial is NP. Again, go back to the cars, right? 0, 1, 2, 3, 4, 5 as the average, in San Diego, the cars. That's not binomial. So you just had to have the probabilities and multiply them out. But when it's binomial, tremendous shortcuts can be taken. NP for mean, NPQ for variance. You like that because it doesn't matter how big the problem is. That calculation is really short and sweet. Okay. Any further questions about anything related to this test?
Nope.
No.
Just gonna unmute yourselves. So Robert's phone, I see is here and Junior's here. Robert, where's your evil looking helmet? Usually that's your icon. I was afraid to meet Robert. I'm like, oh my God, Robert's part of a, outlaw biker gang, obviously. And, he Hell's Angels are afraid of him. I saw that helmet and, I had to look it up on the internet and it said, if you're familiar with this symbol, it's like one of those movies. If you see this symbol, now you're going to get the phone call that says you're going to, bad things. And I don't know, kind of intimidating looking.
No.
And he's a nice guy.
I know Robert's a big teddy bear, except when he's tackling you, I'm sure. I had a student the last few semesters and he was with me on Zoom and his picture was just him being stone faced. But then every time he'd log on, he'd start in that position and everyone would think it's his icon. And then he'd twitch or move or something, and everyone would freak out because he looked exactly like his icon, his picture of himself, but he would always log on and not move for like a minute or two just to mess with everybody. I always thought it was pretty hysterical because sometimes he'd do it and he'd just blink and not move. He had this down. We used to joke because when we couldn't tell when we were looking at him or his picture. We'd look at his picture for a while and be like, he hasn't blinked yet. And then he all of a sudden he'd start talking and say, yes, I always win staring contests, things like that. Right, guys. Well, I think we're a little bit early, so you guys have an extended recess today. So be good on the playground. Again, don't hog the tetherball courts. It's been a problem lately, I hear. And swings, I think 30 seconds is still the max if there's somebody waiting. You guys know how it works. I was parent helper for many, many, many years when my kids were in elementary school. Every other Friday, it felt like all year round. And yeah, had to break up a lot of tetherball conflicts. That was a biggie for elementary school kids.
All right, Professor, you have a good day and thank you for.
All right, you guys, have a great rest of the weekend. Relax, show up ready, and kick some statistics butt. That's all I gotta say.
Do we have to turn in something for Tuesday?
Sorry, say again.
Do we have to turn in something for Tuesday?
Only if you're doing redos.
Oh, okay. Perfect.
I'll bring my Red Bull.
Yeah, bring.
No, I'm gonna make sure I eat this time.
Yes. Eat food. Have some eggs. Something healthy. Some fruit. I don't know. All right. You guys take care of yourselves. Have a great, safe weekend. Okay.
Thank you.
Bye bye.
Bye-bye.